Okay, in this video we're going to talk about measures of central tendency and variation. And out of that section we're going to be computing means, understanding mean as a balance point, computing medians, finding the modes, choosing the most appropriate average, measures of spread, and then also we'll look at box plots. Additionally, we'll talk about outliers, comparing sets of data, variations, which is the mean absolute deviation, which we will not discuss, but we are going to talk about the variance and the standard deviation. Also normal distribution, applications to the normal curve, and percentiles. So as you can see, this is going to be a tall order for this particular section in this particular video. Okay, let's go ahead and go into measures of central tendency. Here we got two important aspects of data are its center and spread. So you have two important aspects, the center and the spread of the data. The mean and median are measures of central tendency that describes where the data are centered. And then you got the range, interquartile range, variance, mean absolute deviation, and standard deviation. They describe the spread of the data and should be used with measures of central tendency. Okay. Let's talk about how to compute means. The number commonly used to characterize a set of data is the arithmetic mean, and it's frequently called the average or the mean. So the arithmetic mean of the numbers x1, x2, all the way up to x sub n is denoted by this symbol x bar, and it's given by this formula. X bar is equal to x1 plus x2 plus x3 all the way up to x sub n divided by n. In other words, you're going to take the sum of the individual data values that you'll have, and whatever that sum is, you're going to divide that by the actual number of data values in that set of data. Okay, just think of it as just taking the average of a certain number of grades. Now, to understand the mean as a balance point, here we got the mean of 5. That's going to be the balance point where the sum of the distances from the mean to the data points above the mean equals the sum of the distances from the mean to the data point below the mean. So this mean is going to be 5. That's going to be our balance point. Okay? So here, this sum of those distances from the mean to those data points has to be the same as the sum of the distances from the mean to the data points below it. Okay? Because the distances above has to be equal to the distances below. And as you can see here, the sum of the distances above the mean, which is 3 plus 5, or 8. And then you take the sum of the distances below the mean, that's 1 plus 2 plus 3, 1 plus 2 plus 2 plus 3, or 8. They're both the same. Okay? As you can see, the distance from 5 to 4, that's 1. The distance from 5 to 3, that's 2. The distance from 5 to 2, that's 3. And here you got two numbers of 3, so that means you have the two 2's here, because you're going to add 2 twice. And then on the right side, the distance from 5 to 8 is 3, and the distance from 5 to 10, that's 5. The sum of those two distances is 8 as well. So that's why the data is centered about the mean, but the mean does not belong to the set of data. Okay. It is possible to rearrange the data to have the same mean, but be spread very differently. Like in this situation here, on the left-hand side, you got 2 plus 3 plus 3 plus 4 plus 8 plus 10. take the sum of those numbers, divide that by 6, you're going to get a mean of 5. But on the other hand, we got -3, -2, -2, -1, 18, and 20. Add those data values together and divide that by 6, you're also going to get 5. Okay, so here the data can be rearranged to have the same mean, but they can be spread out very differently, because here you got positive data values here, but with this set you got 4 of the 6 data values that are negative. Okay, the value exactly in the middle of an ordered set of numbers is called the median. So this is the other type of central tendency. To find the median for a set of numbers, you're going to arrange the numbers in order from least to greatest. And then, if you have an odd set of data values, like let's say 3, 5, 7, 9, an odd number of data values, then the middle number of that ordered set is going to be the median. And if n is even, like 2, 4, 6, 8, 10, an even set of data values means that the median is going to be the mean or the average of the two middle numbers. Okay, so you first place your numbers in order from least to greatest and then find out what the median is. Okay, it's either going to be the middle number if it's an odd set of data values, or the average of the two middle numbers if it's an even number of data values. A median is often reported with the interquartile range, a measure of the spread that shows where the middle 50% of the scores lie with the median in that range. The two together form a much better pair to describe the data than the median by itself. And then next is finding the mode. Okay, it is a set of data that is sometimes reported as a measure of central tendency, but when it's reported in that form, it is frequently being misused. Okay, so your textbook tells you that there are two types of central tendency, the mean and the median, but there are other textbooks that mention the mode as a third measure of central tendency. Okay, but sometimes it's quite often misused. Now, the mode of a set of data is going to be the number that appears most frequently, if there is one. But the mode does not have to be in any way a measure of central tendency. Now, the mode is usually reported when you're dealing with categorical data. So in this example, let's say we want to find the mean, the median, and the mode of this set of data. Here we got 60, 60, 70, 95, 95, and 100. We want to find the mean of this set of data. This is part A. What you're going to do here is you're going to take the sum of these individual data values, as you can see here, and you can count that there are 6 data values here, so we're going to divide by 6. So if we add 60, 60, 70, 95, 95, and 100 together, you're going to get 480. You're going to divide that by 6 because there's 6 data values here. So 480 divided by 6 is going to be 80. So the mean of this set of data is going to be 80. Part B is finding the median of that set of data. Here the data is arranged from least to greatest, and there are an even number of data. So the median, in this case here, you're going to have to take the average of the two middle numbers here, because there's an even number of data values here. Or another way you can do this is to cover up the first and the last numbers in this ordered set, and then cover up the next, and just keep going until you get to the middle, which is 70 and 95. So you have to get the average of those two. Add 70 and 95 together, you'll get 165. Divide that by the 2, you'll get 82.5. So the median of this set of data is 82.5. And to find the mode, in this case, This is an example where you can have more than one mode. In this case, 60 and 95. They both occur the most often. So 60 and 95 are going to be your modes. So here you have two modes. So this set of data is considered to be what they call bimodal. Okay, so it is possible for you to have more than one mode, or you could have no mode at all. Okay, choosing the most appropriate average. Although the mean is the most commonly used, quote, average to describe a set of data, it may not always be the most appropriate choice. Like in this example here. Suppose the company employs 20 people. The president of the company earns $200,000. The vice president earns $75,000, and 18 employees earn $10,000 each. Is the mean the best number to choose to represent the, quote, average salary for the company? Okay, now here's how we can find the mean here. Got the president making $200,000, the vice president $75,000. Then you get 18 employees making $10,000 each. So that's 18 times 10,000. So take 18 times 10,000, that's 180,000 plus the 75,000 plus 200,000, you're going to get 455,000. Divide that by 20 because you got 18 employees plus the vice president and the president, that's 20 altogether. That will give you a mean of $22,750. Now, in this case here, the mean of $22,750 is not representative. So you have to use either the median or the mode, both of which are $10,000, would describe that typical salary a little bit better. And the reason why it's not representative because you got the president making $200,000 and a vice president making $75,000. Those data values are pretty much far away from the $10,000 that the 18 employees make. So you'll be better off using the median or the mode for this particular situation. Here, the mean is affected by extreme values. In most cases, the median is not affected by extreme values. Another example would be, suppose 9 students make the following scores on a test. As you can see here, 30, 35, 40, 40, 92, 92, 93, 98, and 99. Is the mean the best, quote, average to represent, is the median, the best average to represent the set of scores? Well, if you take the median of this set of data, it's going to be the middle number. You can see it's going to be 92. So the median is 92. And by the way, that data is already sorted. So make sure your data values are sorted before you can find the median of that set of data. From that score, one might infer that the students all scored very well, yet 92 is certainly not a typical score. In this case, you want to find the mean, which is 69 approximately. That might be inappropriate than the median itself. However, with the spread of the scores, neither is very appropriate for this distribution. Okay, now is the mode an appropriate average for the following test scores? Here we got 40, 42, 50, 62, 63, 65, 98, and 98. As you can see, 98 is a data value that occurs the most frequent, so 98 is the mode. Again, that mode or that score of 98 would not be representative of the set of data because of the large spread of scores and the much lower mean and the median. Here the scores are very large. You have a wide range of values from 40 all the way up to 98. So the mode would not be a good representative value for that set of data. So now we look at the measures of spread. Let's say we want to consider the following data. Okay. Now, the first measure of spread is the range. The range is the easiest one to compute because we can subtract the lower extreme from the upper extreme. So if we had this set of data, the upper extreme is 35, the lower extreme is 20. 35 minus 20 would give you 15. So 15 would be the range for this set of data. And also they mentioned the mean. You have two numbers in the middle because you have an even set of data. So you add 26 and 27 together and divide by 2. That gives you the 26.5. Okay. Now, this one they talk about the interquartile range. Now with the interquartile range, you talked about two different quartiles. The lower quartile, which is Q1, and the upper quartile, which is Q3. And what you want to do here, to find the lower quartile, you want to take the median of the lower set of numbers here. If you were to split this up evenly, if you want to split these data values evenly, the lower end and the higher end, the lower end you find its median, the higher end you find its median. So in this case here, these are the 5 lowest scores. Find its median, you're going to get 22. These are the remaining upper scores. Find its median, you're going to get 28. And to find that interquartile range, you're going to subtract Q1 from Q3. In other words, you're going to do 28 minus 22, which will give you 6. So the interquartile range here will be 6. Okay, so when the interquartile range is reported along with the median, not only do we know the middle, we know how spread out the middle 50% of the data are. All right, next we'll talk about what a box plot is. A box plot is a way to display data visually and draw informal conclusions. Box plots show only the visual representations of the 5-number summary of the data, the median, the upper and lower quartiles, and the least and greatest values of the distribution. So in this case here, as you can see here, they give an illustration of just pretty much where the median is going to be the middle data value, and then your minimum data point is always on the left side, the maximum data point is on the right side. Q1 represents the bottom 25%, Q3 represents the top 25%. Okay, and then they take those individual data values here, the minimum, then the maximum, then Q1, Q3, Q2 is in the middle. So here you're going to connect a box from Q1 up to Q3 with vertical bars at Q1, Q2, and Q3. Then your whiskers are going to be extended with the maximum to the minimum point on the left side, and then from Q3 up to the maximum point on the right side. That's why they call it a box and whisker plot. In this example, what are the minimum and maximum values, the median and the lower and upper quartiles of the box plot below? Okay, here the minimum, as you can see here, is 0. The maximum is this dot right here. That's 70. So the minimum is 0, the maximum is 70. The lower and the upper quartiles, well, actually, we can talk about that. The lower and the upper quartiles, here's the lower quartile right here. That's this dot where the bar is at. That's 10. Then the upper quartile is going to be this dot right here where the bar is at on the far end. That's going to be 35. The median is going to be this dot that's inside the box. That's 20. Okay, so that's how you identify the minimum and maximum values, the median, and the lower and upper quartiles for any box plot. Next, we'll talk about what an outlier is. An outlier is a value that is widely separated from the rest of the group of data. In the set of scores 91, 92, 92, 93, 93, 93, 94, all data are grouped close together so no values are widely separated. Okay. Okay. So here they're close together because the lowest and the highest, that range is only 3. So that means that those data values are close together. Now let's say we have the same set of scores here. Well, not quite the same set of scores, but now we have 21, then 92, 92, 90, 93, 93, 93, 95, 150. Both the number 21 and the number 150 are widely separated from the rest of the data. So those values would be potential outliers because those two numbers are pretty much far away from the remaining numbers in that set of data. So an outlier is going to be any value that is more than 1.5 times the inner quartile range above the upper quartile, or 1.5 times the inner quartile range below the lower quartile. And we usually indicate an outlier with an asterisk. Whiskers are then drawn to the extreme points that are not outliers. All right, now look at this example here. The table shows the final medal standings for the top 20 countries in the 2008 Summer Olympics. Draw a box plot of the data and identify potential outliers. Okay, now here we got two extreme scores here by looking at this set of data, 11 and 110. There's 110 right here, and there's 11 right here. Those can be considered to be potential outliers. And the median, if you were to sort this data, and which I believe it is, and you find the median of those 20 countries, you have to consider the 10th and the 11th. So you consider 20, I think it's 25 and 27. And they came up with a mean of 26.5. Okay, but here you have to sort that data set of data values, find the median. So that'll be 26 and 25. I mean 26.5 for the median. Q1 is the median of the 10 smallest countries with those medal standings. That's 17. Q3 is the top 10 with, according to the medal standings, that's 43.5. And then the inner quartile range, if you subtract Q3 minus Q1, you're going to get 26.5. Now the outliers are scores that are greater than 43.5, which is the upper quartile, plus 1.5 times the inner quartile, or 26.5. So 43.5 plus 1.5 times 26.5 would be 83.25. And also less than 17 minus 1.5 times the inner quartile range of 26.5. Here Q1 is 17. Minus 1.5 times 26.5 will give you negative 22.75. Okay, so if you were to look at that data, you can see that 100, 10, and 100 are bigger than 83.25. So those two data values will be considered outliers. Okay, and this is what the box and whisker plot will look like for that set of data. The lowest was 11, the highest was in this particular case, they're going to consider 72 as the highest. Because these two are outliers here. They're denoted by asterisks. And of course, this is your Q1, which is 17. Q3 is 43.5. The median is 26.5. Okay, how can we compare sets of data? Box plots are used primarily for large sets of data or for comparing several distributions. The stem and leaf plot is usually a much clearer display for a single distribution. Parallel box plots are drawn using the same number line. Using the same number line gives us the easiest comparison of medians, extreme scores, and the quartiles for the sets of data. Although we cannot spot clusters or gaps in a box plot as we can with stem and leaf or line plots, we can more easily compare data from different sets. With box plots, we do not need to have sets of data that are approximately the same size as we did for stem and leaf plots. To compare data from two or more sets using their box plots, first study the boxes to see if they are located in approximately the same places. Next, consider the lengths of the boxes to see if the variability of the data is about the same, and also check whether the median, the quartiles, and the extreme values in one set are greater than those in another set. Okay, so here from the box plot, we can see that the mean salaries for males have been higher than those for females. Okay, so here you can see the one for male and this one for females. You can see those mean salaries are pretty much higher. Since the extreme values, median, and quartiles for males are greater than those for females. Also, more than 50% of the mean salaries for males are greater than those for the mean salaries of females over the time period. Okay, we'll first talk about variation. Now, the only thing I'll talk about is the variance and the standard deviation. I won't talk about the mean absolute deviation. A measure spread is needed when data are summarized with a single number, such as the mean or the median. The simplest way is to find the range. We can also use the interquartile range, or the IQR. The most sophisticated is the standard deviation. The variance and standard deviation are two commonly used statements of dispersion. The measures are also based on how far the scores are from the mean. Okay, now to compute the variance, which they call lowercase v, of n numbers, we can do that as follows. We first find the mean of the numbers. Then number 2, you're going to subtract the mean from each number. Then number 3, you're going to square each difference found in step 2. And then step 4, find the sum of the squares in step 3. Number 5, divide the sum in step 4 by n, which is the number of data values, to obtain the variance. And once you find the variance, finding the standard deviation is going to be easy because you're going to take the variance and get a square root. Because here the standard deviation of something is always going to be equal to the square root of the variance. Okay, so here the standard deviation, which is going to be lowercase s of n numbers, is the square root of the variance, as you can see here. Now, later on, I'm going to introduce you another way of finding the variance and the standard deviation. Professor Abel gave 2 group exams. Exam A had grades of 0, 0, 0, 100, 100, 100, and Exam B had grades 50, 50, 50, 50, 50, 50. Find the following for each exam. You want to find the mean for exam A and for exam B? Well, for the mean, you just take the sum of these 6 numbers, divide by 6. So if we add these, you're going to get 300. Divide that by 6, you're going to get 50. So for exam A, the mean is 50. For exam B, that's also easy because you just add these numbers here, add those 50, add the score of 56 times, that's 300, divided by 6, you're going to get 50. So the mean there is also going to be 50. Part B is found in the range. For exam A, the lowest is 0, the highest is 100. 100 minus 0, that's 100. For exam B, the lowest and the highest are the same. So if you do 50 minus 50, you're still going to get 0. So the range for exam B will be 0. Okay, now I won't discuss the mean absolute deviation here. But for the standard deviation, now the way they did this was they subtracted the mean from each of the individual scores here. So here we have 3 zeros, so they did 3 times 0 minus 50 and then squared, plus 3 scores of 100, so they did 3 times 100 minus 50, and that's going to be squared. And all that's going to be divided by 6. And that's all underneath the radical, so you'll take the square root of it after you complete all of this to get the standard deviation of 50 for test A. Now for exam B, of course, the mean is the same as all the test scores. So if we do 6 times 50 minus 50, that's 0. Square root is 0 times 6 is 0. 0 divided by 6 is 0. The square root of 0 is 0. So the standard deviation is 0. Okay, and then the median for exam A, the two middle numbers here are 0 and 0 and 100. 100 and 0 is 100 divided by 2 will give you 50 for the median. For exam B, they're all 50, so the median is obviously going to be 50. Okay, and then they computed the interquartile range by taking the now if you split, let's say for exam A, if you split this in half, this bottom half has a median of 0. This upper half has a median of 0. I mean of 100. So 100 minus 0 will give you the 100. And then for exam B, split this in half. The bottom half has a median of 50. The upper half has a median of 50. 50 minus 50 is 0. So the interquartile range there is 0. All right, next is normal distributions. The graphs of normal distributions are the bell-shaped curves called normal curves. And a normal curve is a smooth bell-shaped curve that depicts frequency values distributed symmetrically about the mean. So the mean, the median, and the mode will all have the same values. And I'll draw an illustration of a normal curve. So pretty much the normal curve will look somewhat like this. It's not the best, but it looks somewhat like this. So here it is symmetric, meaning the left side has the mirror image of the right side. So here the mean, the median, and the mode are all in the middle. The curve extends infinitely in both directions and gets closer and closer to the x-axis but never reaches it. The curve is symmetrical about its center point, but not all symmetrical distributions are normal. Okay, and this is the breakdown of what the normal curve is. In this particular case here, you're going to see here's the mean that's in the middle. That's the center of this normal curve, and I'm going to explain what these percentages mean. Okay. Now, the 68%, which is split up by 34% and 34%, that 68% tells us that 68% of the data values lie within one standard deviation of the mean. That's basically what this is. Sometimes they call this the empirical rule for a normal curve. Okay, the empirical rule is this. 68% of the data values lie within one standard deviation of the mean. And then you have 95% of the data values, they lie within two standard deviations of the mean. Okay. So with 68% here within one standard deviation here, if you were to split this up evenly by 2, 68 divided by 2, that's 34% on the left and 34% on the right. And then for 95%, we already have 68%. So subtract 68%, and from 95%, you're going to get 27%. Divide 27% by 2, you're going to get 13.5% on the left and on the right. And then finally, 99.8% of the data values lie within 3 standard deviations of the mean. Okay. Subtract 95% from the 99.8%, you're going to get 4.8%. Divide that by 2, you're going to get 2.4% on the left and on the right. Okay. And the rest is this 0.1 and 0.1% on the left and the right. That makes up the remaining 100% of that curve. Okay, on a normal curve, about 68% of the data values lie within one standard deviation of the mean. About 95% lie within 2 standard deviations, and about 99.8% are within 3 standard deviations. The percentages represent approximations of the total percent of area under the curve. Okay, when a standardized test was scored, there was a mean of 500 and a standard deviation of 100. Suppose that 10,000 students took the test and their scores had a bell-shaped distribution, making it possible to use a normal curve to approximate the distribution. So in this case here, how many scores are between 400 and 600? Okay, so now what I'm going to do is draw the normal curve. And we're told that the mean was 500. Okay, and we want to find out how many scores are between 400 and 600. Okay, and the standard deviation, by the way, is 100, so we know if we do this. One standard deviation to the right, this will be 600. Another standard deviation will be 700, and another standard deviation will be 800. That's to the right. And to the left, if we subtract 500 minus 100, that'll be 400. Subtract another 100, that'll be 300. Subtract another 100, that'll be 200. So in other words, we want to find out how many scores are between 400 and 600. So here's 400, and here's 600. We want to find out how many there are. Notice that 400 and 600 represent one standard deviation away from the mean. Those numbers are within one standard deviation of the mean. And according to the empirical rule, 68% of those data values lie within one standard deviation of the mean. So we'll take 68% of 10,000, or 0.68 times 10,000. Multiply that out, you'll get 6,800. So that means that 6,800 students scored between 400 and 600. And how many scored between 300 and 700? Okay. Let's go back to this normal curve that I just drew between 300 and 700. Here's 300 and here's 700. Those those numbers are within 2 standard deviations of the mean, which means 95% of those data values lie within 2 standard deviations of the mean. So we take 95% of 10,000, which will be 9,500. So that means that 9,500 students scored between 300 and 700. And how many scored between 200 and 800? Let's go back to this again. 200 is way over here. 800 is way over here. Those two data values are within 3 standard deviations of the mean. And according to the empirical rule, 99.8% of those data values are within 3 standard deviations of the mean. So take 99.8% of 10,000, or 0.998 times 10,000, you'll get 9,980. So 9,980 students scored between 200 and 800. And then part D, how many scored above 800? Well, that's this piece past 800 right here. And we know that's going to be 0. We know that represents 0.1% on the right, and this small piece on the left represents 0.1% on the left. So if you take 0.1% of 10,000, you're going to get 10. So 10 students scored above 800. Okay, let's look at some applications of the normal curve. Suppose that a group of 200 students ask their teacher to grade, quote, on the curve. Okay, so if you were to ask your teacher to grade on the curve, then that means that this will be the normal curve that they will use to give you your grade. Let's say if the mean on the test was 71 and the standard deviation was 7. The graph shows how the grades could be assigned. So in other words, if you ask your teacher to grade on the curve, then that means your teacher will have to find out what the average of all the scores of all the students in that class and find out what the standard deviation is. That way, your instructor will give you that grade based on that normal curve. Okay. So in this case here, the mean was 71. The standard deviation is going to be 7. So that means 68% of the students in that class will get a grade of C. The upper 13.5% of the class will get a B, and the upper 2.5% of the class will get an A. The lower 13.5% will get a D, and the lower 2.5% will get an F. So in other words, here's what that means. One standard deviation to the right will be a grade of 78. Another standard deviation to the right will be an 85. So in other words, if you have a grade of 85 or above, you'll get an A. If it's less than 85 but greater than 78, you'll get a B. Now, of course, the mean is 71. Subtract 71 from 7, you'll get 64. Then subtract another standard deviation. 7 from 64 will be 57. So if your grade is less than 57, you're going to get an F. If your grade is from 57 up to 64, you'll get a D. And between 64 and 78, it will be a C. Okay. Based on the normal curve, the table shows the range of grades that the teacher might assign if the grades are rounded. Okay, so here's what that test score is. 85 or above is an A, 78 to 84 is a B, 64 to 77 is a C, 57 to 63 is a D, anything less than 57 is an F. Okay, and this is the number of people per grade. and the percentages. Okay, next we'll talk about percentiles. When students take a standardized test such as the ACT or SAT, their scores are often reported in percentiles. A percentile shows a person's score relative to other scores. Percentiles divide the set of data into 100 equal parts. Deciles are points that divide a distribution into 10 equally spaced sections. And the rth percentile is always represented by P sub r. So in this particular example here, a standardized test that was distributed along a normal curve had a mean of 500 and a standard deviation of 100. The 16th percentile is 400 because 400 is one standard deviation below the mean. Find P sub 50 and P sub 84. Now here 500 is going to be the median, and 50% of the distribution is less than 500, so P sub 50 would be 500. Now you're told that 600 is going to be, well, 400 is one standard deviation below the mean, so that means 600 must be one standard deviation above the mean. And 84% of the distribution is less than 600, so P sub 84 will have to be 600. Okay. Here's another example. Aussie was ranked 25th in a class of 250. What was his percentile rank? Here there were 250 minus 25 because he was ranked 25th in the class, so that means you subtract 25 from 250. That means 225 students in his class were ranked below Aussie. So that means if you take that 225, divide that by the number in the class altogether, that's 250, you're going to get 90%, which means 90% of his class was ranked below him. So that means Aussie is ranked in the 90th percentile. Okay. And in part B, in a class of 50, Kathy has a percentile rank of 60. What was her class standing? Okay. She was ranked in the 50th, in the 60th. Well, she's ranked with a percentile rank of 60. That's the 60th percentile, meaning 60% of her class ranks below her. So that means you take 60% of the number in the class, which is 50. So 60% of 50, or 0.60 times 50, will give you 30, which means 30 students ranked below Kathy. Subtract 30 from the 50, you're going to get 20. So that means that Kathy is 20th in her class. That's her ranking. Okay, so this will conclude this particular video that deals with the measure of central tendency and variation.